Biologists can map the molecular structure of a cell down to the last atom, but ask them to define life itself, and the consensus fractures. Every definition seems to have an inconvenient specimen attached to it. Look at these two systems under high magnification. On the left, churning mud. On the right, a bacterium moving with clear direction. Chemically, they are nearly identical. Both are constructed from the exact same primary elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The problem we face is conceptual. Life is not a substance like gold or salt that you can isolate and identify with a simple chemical reagent. The atoms that compose an organism are the same ones that compose dirt or air. The difference is the pattern of their relations. Life is a highly specific mode of organization, maintained continuously through historical inheritance and a constant flow of energy. A biological system is never truly static. Biological order is essentially a verb wearing the clothes of a noun. To maintain that order, life must constantly fight entropy, the physical tendency of all matter to disperse into random, uncoordinated states. A living system acts as a historically continuous chemical organization that actively resists this natural slide towards disorder. The enzymes, membranes, and pathways that keep a cell intact didn't assemble by chance. They descend from previous successful arrangements. It is chemistry with a memory. To understand how a living thing persists, we have to look for the precise physical and informational constraints that keep its chemistry from simply drifting apart into smoke. Maintaining this highly constrained internal order has a strict thermodynamic cost. It requires a continuous, open exchange with the surrounding environment. This diagram illustrates a bounded biological system. Energy-rich matter and signals flow into the boundary, while heat and waste are exported out. By coupling these flows to chemical reactions, the cell pays for internal order by increasing environmental disorder. Biology doesn't violate the laws of thermodynamics. It strikes a local, temporary bargain, purchased entirely through this open exchange. Relying on energy flow often tempts people to define life by single properties, like metabolism, but we encounter immediate problems. Look at a candle flame consuming wax next to a cell metabolizing glucose. The flame consumes fuel and maintains a distinct structure for a while, but it lacks any internal regulation, and it carries no historical instructions for making a successor. If we define life by growth and order, we hit a similar wall. A crystal lattice growing in a supersaturated solution mimics biological expansion perfectly, yet the crystal fails the test because it does not have an autonomous metabolism, nor does it maintain a selective boundary to regulate what enters and exits. Even reproduction fails as a strict, universal requirement for individual living things. A sterile worker ant and a mule are clearly alive, despite leaving no direct descendants. No single sign of life is sufficient on its own. Biology operates as a constitutional settlement among several interacting criteria, rather than a monarchy ruled by one. To accurately judge whether an entity is alive, we must evaluate it across 5 specific, rigorous criteria. This diagram maps the 5 themes of living systems. A selective boundary separates the inside, while metabolism processing energy. Inside, DNA stores information directing chemistry, and reproduction ensures lineage survival. Finally, regulation maintains internal homeostasis against external disturbances. Any one of these criteria alone is merely an anecdote. It is the continuous, organized interaction among all 5 that forms the definitive argument for life. We can apply this exact framework to real-world edge cases to understand exactly where traditional definitions begin to break down. This heat map scores entities across the 5 criteria. Darker colors indicate stronger traits. The virus scores highly on information, but is blank on autonomous metabolism, borrowing host machinery instead. Conversely, the mule scores perfectly in metabolism and regulation, but fails entirely in reproduction. These edge cases clarify the architecture of the concept. Reproduction, for instance, is a necessary property of the evolutionary lineage, even if it is not a requirement for every individual member of that lineage. When an entity fails one or more criteria, the borderline category is not a biological defeat. Instead, it serves as a precise map of dependency. This chart compares the operational autonomy of a bacterium against a virus and a mitochondrion. The mitochondrion retains distinct signs of bacterial ancestry and performs essential metabolic functions, but it traded away its independent boundary to become an integrated component of a larger cell. Biological individuality is rarely absolute. It is frequently an organized compromise, built from the integration of formerly independent, free-living lineages. This principle of organized dependency scales upward. Biological explanation begins with molecules and cells, but it climbs through tissues, organisms, populations, and entire ecosystems. Even at the planetary scale, those exact same rules of historical organization, physical constraint, and energy flow dictate what is possible. When we zoom out to the biosphere as a whole, the collective activity of these microscopic systems maintains the chemical balance of the planet itself. A living system, at any scale, is a bounded, historically continuous chemical organization that transforms energy and matter to maintain itself, while participating in an evolutionary lineage. Biology is the science of what can happen to these systems under strict material limits. It lives in the negotiated ascent between isolated chemistry and global ecology.